At 1,000 hours on September 23, 1942, General Leslie Groves sat in an office in Washington, D.C., receiving authorization to command the Manhattan Project America's program to build an atomic bomb. Groves was 46 years old, an Army Corps of Engineers officer who had just overseen construction of the Pentagon. He knew large-scale construction. He understood military bureaucracy, but nothing had prepared him for what he was about to demand. Within weeks, Groves would be requesting resources that competed directly with every other American war program. He would demand enough electricity to power a city of 500,000 people, more than the entire American automobile industry consumed. He would require 14,700 tons of silver borrowed from the U.S. Treasury to use as electrical conductor because copper was too scarce. He would need uranium from mines in Colorado, Canada, and the Belgian Congo. He would require land the size of Rhode Island for facilities in Tennessee, Washington State, and New Mexico, and he would need all of it immediately, with highest priority over every competing demand. The authorization Groves received was unprecedented. The Manhattan Project would have AAA priority, the highest priority rating in American war production. Any resource the project needed would be diverted from other programs. Any facility the project required would be built regardless of competing demands. Any scientist, engineer, or skilled worker the project wanted would be assigned regardless of where they currently worked. The military services, Army, Navy, Army Air Forces would provide manpower, security, transportation, and logistical support. Cost was explicitly no object. Success was the only metric. But Groves had no guarantee of success. The physics underlying atomic weapons was understood theoretically, but unproven practically. No one had ever built an atomic bomb. No one knew if an atomic bomb could be built. German scientists were reportedly working on atomic weapons. British scientists believed atomic bombs were possible. American scientists believed atomic bombs were essential to winning the war, but belief was not certainty. The Manhattan Project was gambling billions of dollars and massive resources on weapons that might not work. The resource demands became clear immediately. The project required 3 separate pathways to produce fissionable material electromagnetic separation of uranium isotopes, gaseous diffusion of uranium, and plutonium production in nuclear reactors. Each pathway required enormous industrial facilities. The electromagnetic separation plant, later called Y-12, would be built at Oak Ridge, Tennessee. The gaseous diffusion plant K-25 would be built at the same location. The plutonium production reactors would be built at Hanford, Washington. Each facility would consume resources on industrial scales. Oak Ridge's electrical requirements were staggering. The Y-12 electromagnetic separation plant required 238 megawatts of electrical power to operate the Calutron's massive electromagnets that separated uranium-235 from uranium-238. For comparison, the entire Ford Motor Company, every factory, assembly line, and facility consumed approximately 60 megawatts. General Motors consumed approximately 80 megawatts. Chrysler consumed approximately 40 megawatts. The 3 largest automobile manufacturers in America combined consumed less electricity than one Manhattan Project facility. The K-25 gaseous diffusion plant required even more power, 100 megawatts initially, expanding to 238 megawatts at full operation. The Hanford plutonium reactors required additional megawatts. Total Manhattan Project electrical consumption approached 600 megawatts, approximately 1% of total American electrical generation capacity in 1943. The Tennessee Valley Authority had to expand capacity specifically to power Oak Ridge. Bonneville Power Administration had to divert Columbia River hydroelectric power to Hanford. The electrical demand was not just large, it competed directly with aluminum production for aircraft, steel production for ships, and every other electricity-intensive war industry. Military leaders immediately objected. Lieutenant General Brand Somerville, commanding Army Service Forces, questioned whether atomic bomb development justified consuming 1% of national electrical capacity. The electricity going to Oak Ridge could power aluminum smelters producing material for 40,000 aircraft annually. It could power steel mills producing armor for 10,000 tanks. It could power shipyards building hundreds of Liberty ships. Was uncertain atomic bomb worth sacrificing certain aircraft, tanks, and ships? Groves argued that atomic bombs, if successful, would end the war. One bomb might destroy an entire city. 10 bombs might force Japan to surrender without invasion. The strategic value justified the resource cost, but Groves could not guarantee success. He could only argue that the potential justified the attempt. The counter-argument was that resources spent on uncertain weapons were wasted if the weapons never materialized. Resources spent on proven weapons, aircraft, tanks, ships produced tangible combat capability immediately. The debate revealed fundamental tension in military resource allocation. Invest in proven technologies that produce incremental advantages, or invest in revolutionary technologies that might produce war-winning breakthroughs. The proven approach was safer but limited. The revolutionary approach risked wasting resources on failures, but offered potential for decisive advantage. The Manhattan Project represented maximum commitment to revolutionary approach, betting billions on unproven technology. The copper shortage created another conflict. Manhattan Project facilities required massive quantities of copper for electrical conductors. Copper was the second scarcest strategic material after rubber. Military demand far exceeded supply. Every pound of copper going to Manhattan Project was copper not available for ships, aircraft, electronics, or ammunition. The project needed approximately 14,700 tons for Y-12 alone. The military services were desperate for copper to build ships and aircraft. Giving copper to unproven atomic bomb program meant reducing production of proven weapons. Groves solved this by borrowing silver from U.S. Treasury. Silver conducts electricity nearly as well as copper. The Treasury held approximately 47,000 tons of silver as monetary reserve. Groves requested 14,700 tons, received 14,700 tons, and used silver instead of copper for electromagnetic coils at Y-12. The substitution worked, but highlighted the project's resource consumption. When a project requires borrowing national monetary reserves, the scale is extraordinary. Uranium presented different challenges. Natural uranium contains 0.7% uranium-235, the fissionable isotope needed for atomic bombs. The remaining 99.3% is uranium-238, which is not fissionable. Separating isotopes required processing hundreds of tons of uranium ore to produce pounds of weapons-grade U-235. The ore had to be mined, refined, processed, enriched. Each step consumed resources and competed with other demands. American uranium came primarily from mines in Colorado and Canada. Belgian Congo had the world's richest uranium deposits, but accessing them required securing mining operations in Africa and transporting ore across submarine-infested Atlantic. The logistics were complex and dangerous. Uranium shipments required military security to prevent German interception. The entire supply chain competed for shipping, labor, and military protection that could have supported other operations. Plutonium production required building nuclear reactors, technology that did not exist in 1942. The Hanford site in Washington state was chosen because it had Columbia River water for cooling, Bonneville power for electricity, and isolation for safety. Building 3 production reactors required constructing entire industrial city in remote location, housing for 50,000 workers, roads, railways, power lines, water systems, security fencing. The construction program competed directly with building air bases, shipyards, and training facilities for conventional forces. The scientific manpower requirements created another conflict. The Manhattan Project needed the best physicists, chemists, and engineers in America. Many were already working on other critical war programs. Radar development needed scientists. Proximity, fuse development needed scientists. Rocket development needed scientists. Code breaking needed mathematicians. Every program wanted the same limited pool of qualified personnel. Groves rated other programs ruthlessly. If he needed a scientist working on radar, he requested transfer using 8AA priority authorization. The scientist would be reassigned to Manhattan Project regardless of radar program needs. Many scientists transferred willingly. Atomic weapons were intellectually fascinating. Others transferred reluctantly, believing their current work was more immediately valuable. But AAA priority meant transfers were not negotiable. The VT Proximity Fuse program, which developed artillery shells that detonated near targets rather than requiring direct hits, lost scientists to Manhattan Project. The Fuse program was producing proven weapons that increased artillery effectiveness dramatically, but scientists transferred to work on theoretical atomic weapons that might never exist. The trade-off was strategically questionable, but inevitable given Manhattan Project's priority. The radar program faced similar losses. Radar was revolutionizing air defense, naval operations, and bombing accuracy. Improved radar systems required continued development, but when Manhattan Project needed radar engineers for instrumentation work, the engineers were transferred. The radar program continued with reduced personnel, which delayed improvements that would have enhanced combat effectiveness immediately. The aggregate cost was approximately $2 billion in 1940s dollars, roughly $30 billion in 2024 dollars. This represented 0.4% of total American wartime expenditure of approximately $500 billion. The percentage seems small, but context matters. $2 billion in 1940s dollars could have purchased 1,000 B-29 Superfortress bombers at approximately $500,000 each, 30 Essex-class aircraft carriers at approximately $70 million each, 40,000 M4 Sherman tanks at approximately $50,000 each, 200 Fletcher-class destroyers at approximately $10 million each, ammunition, fuel, and supplies for multiple field armies for an entire year. The opportunity cost was enormous. Every dollar spent on Manhattan Project was dollar not spent on conventional weapons that would definitely be used in combat. The project consumed resources that could have equipped dozens of divisions, built hundreds of ships, produced thousands of aircraft. The gamble was that one or two atomic bombs would be worth more strategically than thousands of conventional weapons tactically. Military commanders disagreed about whether the gamble was justified. General George Marshall, Army Chief of Staff, supported Manhattan Project as potentially war-winning technology. Admiral Ernest King, Chief of Naval Operations, was skeptical about diverting resources from proven naval programs to uncertain atomic weapons. General Henry Arnold, commanding Army Air Forces, supported the project because strategic bombing was Army Air Force's mission and atomic bombs were ultimate strategic weapons. But Arnold also worried about resources diverted from conventional bomber production. The skepticism was understandable. In 1942 and 1943, victory was not assured. Germany still controlled most of Europe. Japan controlled most of the Pacific. American forces were fighting desperately in North Africa, at Guadalcanal, in the Atlantic. Every resource mattered immediately. Diverting resources to program that might not produce weapons until 1945, if ever, seemed wasteful when those resources could produce weapons needed in 1943. But Roosevelt and his science advisors believed Germany was pursuing atomic weapons. If Germany succeeded first, the war might be lost regardless of conventional force levels. American atomic bomb program was insurance against German atomic breakthrough. Even if American bombs were never used, the program was justified by preventing German monopoly on atomic weapons. The strategic calculation was not just about what American bombs would accomplish, but about preventing what German bombs would accomplish. The intelligence on German atomic program was fragmentary and concerning. German scientists had discovered nuclear fission in 1938. German research into nuclear weapons was confirmed through multiple intelligence sources. The scale of German efforts was uncertain, but the existence was confirmed. British intelligence believed Germany was pursuing atomic weapons seriously. American intelligence agreed. The possibility that Germany might achieve atomic weapons first was unacceptable. This fear justified Manhattan Project's priority despite resource consumption. If Germany developed atomic bombs and America had not pursued its own program, the decision would have been catastrophic. Better to spend resources on atomic program that might fail than to risk German atomic monopoly. The precautionary logic overrode concerns about resource allocation. But the precautionary logic created difficult subordinate decisions. If atomic bomb program had highest priority, which programs had second priority? Third priority. How were resources allocated among competing essential programs? The military services fought constantly over priorities. Navy needed ships, Army needed tanks, Army Air Forces needed aircraft, Manhattan Project needed electricity, copper, uranium, scientists. Something had to give. The resolution mechanism was controlled materials. Plan a system for allocating scarce materials among competing programs based on assessed strategic value. The War Production Board administered the plan, but priorities were set politically based on military requirements and presidential direction. Manhattan Project's AAA priority meant it was never subordinated. Other programs fought for second-tier priorities and absorbed the resource constraints. Aircraft production absorbed some constraints. Aluminum was scarce because electrical capacity for smelting was limited. Manhattan Project's electrical consumption reduced electricity available for aluminum production. Aircraft production targets were adjusted downward slightly to accommodate the constraint. The reduction was small, perhaps 2,000 fewer aircraft in 1943, but those 2,000 aircraft might have made tactical differences in combat operations. Shipbuilding absorbed constraints through delayed schedules. Steel shortages caused by copper diversion meant some ship construction was delayed by weeks or months. The delays did not prevent ships from being built. America built 2,700 major warships during World War II. But some ships commissioned in 1944 might have commissioned in late 1943 without Manhattan Project resource consumption. The delay potentially affected operational planning for specific campaigns. The trade-offs were rarely explicit. No one said we're building one fewer aircraft carrier to fund Manhattan Project. But the aggregate resource consumption meant fewer resources available for other programs. The reductions were distributed across many programs in small amounts that individually seemed insignificant, but cumulatively represented substantial opportunity costs. The Trinity test on July 16, 1945, vindicated the resource allocation. The test demonstrated that atomic bombs worked. The physics was correct. The engineering was adequate. The enormous resource investment had produced functional weapons. The successful test transformed retrospective assessment of Manhattan Project from questionable gamble to justified success. But the retrospective assessment obscured the uncertainty present throughout the project. From September 1942 through July 1945, no one knew if atomic bombs would work. Scientists believed they would work. Engineers were building facilities assuming they would work, but belief and assumption were not certainty. The project might have failed for numerous reasons. Physics might have been wrong. Engineering might have been inadequate. Fissionable material production might have been insufficient. Weapon design might have been flawed. If Manhattan Project had failed, the $2 billion massive resource consumption would have been wasted. The resources could have produced conventional weapons that would have been used in combat. The electrical capacity could have powered aluminum production for 80,000 aircraft. The copper could have built hundreds of ships. The scientists could have developed improved radar, better proximity fuses, advanced rockets. The opportunity costs would have been permanent losses with no compensating gain. The successful test and subsequent combat use of atomic bombs at Hiroshima and Nagasaki made the costs seem justified retrospectively. 2 bombs killed approximately 200,000 people and contributed significantly to Japanese surrender without invasion. The invasion of Japan was estimated to cost hundreds of thousands of American casualties. If atomic bombs prevented invasion, the resource cost was minimal compared to lives saved. But this calculation was impossible in 1942 when resources were committed. The decision to fund Manhattan Project was made without knowing bombs would work, without knowing they would be needed, without knowing invasion of Japan would be planned. The decision was made on uncertain estimates of technical feasibility and strategic value. The decision happened to be correct, but correctness was not foreordained. Post-war analysis examined Manhattan Project resource allocation for lessons about funding uncertain programs. The consensus was that revolutionary technologies require accepting risks that proven technologies do not. Manhattan Project succeeded partly because it received resources without restriction. If resources had been limited or conditional on interim progress, the project might have failed from insufficient scale. Revolutionary programs need commitment at levels that seem wasteful if the programs fail but appear prescient if they succeed. The electricity consumption became famous analogy for Manhattan Project scale. Oak Ridge consumed more electricity than most American cities. The K-25 gaseous diffusion plant was the largest building under one roof in the world when constructed 2 million square feet, requiring 5,000 tons of structural steel, operating 24 hours daily, consuming enough electricity to power 500,000 homes. The scale was industrial, not experimental. This was mass production of weapons that did not yet exist. The 14,700 tons of silver borrowed from Treasury became another famous detail illustrating project's unusual demands. The silver was returned after the war. The Treasury required return of monetary reserves. But for 3 years, American atomic bomb program operated using silver conductor coils because copper was too scarce for conventional approach. The substitution worked, but highlighted the project's consuming resources that normal programs could not access. Uranium procurement remained classified long after other Manhattan Project details were revealed. The global supply chain extending from Colorado to Belgian Congo, the security required for shipments, the diplomatic efforts to secure mining rights, the competition with German attempts to secure same resources all remained secret. The uranium supply chain was logistical achievement comparable to building the facilities themselves. The scientific personnel recruitment also remained partially classified. Which scientists transferred from which programs was sensitive information because it revealed priorities within classified defense research. But the general scale was known. Approximately 130,000 people were employed by Manhattan Project at peak, including scientists, engineers, technicians, construction workers, security personnel, and administrative staff. The payroll was comparable to major industrial corporation. The geographic footprint was enormous. Oak Ridge occupied 59,000 acres. Hanford occupied 670 square miles. Los Alamos occupied 45,000 acres. Total land area controlled by Manhattan Project exceeded 1,000 square miles, comparable to Rhode Island. The land was secured through various mechanisms including federal acquisition, military reservation, and involuntary evacuation of existing residents. Entire communities were displaced to build Manhattan Project facilities. The security requirements consumed resources independently of technical requirements. Protecting 3 enormous facilities required thousands of security personnel, hundreds of miles of fencing, communication systems, counterintelligence operations, and classification systems that prevented workers from understanding what they were building. Most Oak Ridge workers did not know they were enriching uranium for atomic bombs. They knew they were processing material for war purposes, but not specifically what. The compartmentalization prevented security breaches, but required duplicating information across groups that could not communicate. The opportunity costs of Manhattan Project were never fully calculated, because doing so would require determining what was not built, because resources went to atomic bombs. Some calculations are possible. Electricity that powered Oak Ridge could have powered aluminum production for X aircraft, but second-order effects are harder to calculate. Did Manhattan Project delay invasion of Japan by consuming resources that could have supported earlier operations? Did it delay victory in Europe by diverting resources from European theater? The questions are unanswerable because counterfactuals cannot be tested. What is certain is that 0.4% of American war expenditure consumed outsized resources in specific categories. Electrical generation capacity was 1% consumed by one program. Scientific talent was substantially concentrated in one program. Exotic materials like uranium and heavy water were almost entirely devoted to one program. The concentration created bottlenecks elsewhere that were absorbed through reduced production or delayed schedules. Military leaders who questioned Manhattan Project priorities in 1942 and 1943 were vindicated in their concerns about resource consumption. The project did consume enormous resources that could have produced proven weapons, but they were wrong about strategic outcome. Atomic bombs ended the war more decisively than any number of conventional weapons could have. The resource gamble succeeded spectacularly. The lesson for resource allocation in uncertainty is that revolutionary programs require commitment that seems irrational if programs fail, but obvious if they succeed. Manhattan Project received resources that rational allocation would not have provided based on probability-weighted outcomes, but the commitment enabled success that rational allocation would have prevented. The paradox is that revolutionary programs need irrational commitment to achieve rational success. The competing priorities that Manhattan Project dominated were not trivial. Aircraft production, shipbuilding, conventional weapons, all were essential to winning the war. Reducing any of these programs risked tactical defeats that could have strategic consequences. But prioritizing proven over revolutionary guaranteed incremental progress without possibility of breakthrough. Manhattan Project represented choosing breakthrough possibility over incremental certainty. The choice was made at highest levels, Roosevelt personally, with advice from science advisors and senior military leaders. The choice was not made democratically. Congress did not vote on Manhattan Project. The expenditure was concealed in military budgets under false descriptions. Democratic accountability was sacrificed for security and speed. The sacrifice was justified by success, but created precedent for executive programs funded without congressional oversight. Post-war, Manhattan Project's success validated the approach. When new revolutionary programs were proposed, thermonuclear weapons, ballistic missiles, satellites, the Manhattan Project model was invoked. Give programs adequate resources, priority over competing demands, insulation from political interference, and expect revolutionary results. The model worked for some programs, failed for others, but became template for how America funds revolutionary technology. The resource allocation decisions that determined Manhattan Project's priority over everything else were political decisions based on technical advice about uncertain outcomes. The decisions happened to produce weapons that decisively influenced war's end, but the decisions could have produced expensive failure if physics or engineering had been wrong. The difference between success and failure was narrower than participants realized and narrower than retrospective analysis suggests. This was Manhattan Project's hidden story, not the scientific achievement or the weapons themselves, but the resource allocation decisions that enabled the achievement, the choice to give one uncertain program priority over dozens of proven programs, the choice to consume 1% of national electrical capacity for facilities that might produce nothing, the choice to borrow Treasury silver because copper was too scarce, the choice to spend $2 billion, 0.4% of war expenditure, on weapons that might not work. The choices that seemed questionable in 1942, risky in 1943, anxious in 1944, and vindicated in 1945. The choices that determined which weapons programs got priority and therefore which weapons were built and which weapons were not built. The impossible choices that leaders made in uncertainty that determined how the war ended.